Hi mathematicians, Caitlin Henderson here with your Unit 6 Lesson 7 video on parallelogram proofs. So to start off, what's a quadrilateral and what is a parallelogram? Quadrilateral is just a four-sided figure, four-sided shape, okay? Polygon, right? We can use a bunch of different words to explain it, but basically you got four sides and it's closed, it's a quadrilateral. Now, a parallelogram is more specifically a four-sided shape, but the opposite sides are parallel to each other. So quadrilateral is kind of this big picture, and then we've got the quadrilateral is the big picture, and parallelogram is that subcategory. So we are told that parallelograms have congruent or parallel sides, but are they congruent? Are the angles congruent? What can we show with the information that we have been given so far? Now, in order to write proofs, we need to know what information we already know. In our text, we're going, lesson by lesson and slowly but surely proving different theorems, different postulates, right? And we don't need to reprove those in our new proofs. We're already using them by, solving for sides that are equal or angles that are equal to each other, right? Being able to identify all the angles in a figure, we're already doing that. Let's talk about some of them that were needed when we're going to do proofs with parallelograms. Okay, corresponding angles are angles that are located in the same quadrant when we draw little squares around the vertex, right? Both of these are located in the upper left-hand corner. These are corresponding angles. Corresponding angles postulate tells us that they're congruent. So if we want to make the statement that corresponding angles are congruent, first we need to identify them based off the definition and then use the postulate to show that they are congruent. Up next, we've got alternate interior angles. So alternate interior angles are angles that are found on the inside of two parallel lines, okay, inside of two parallel lines, and they sit on opposite sides of the transversal. We can use so many different lines and transversals based off of our pictures, especially with our pictures with parallel lines or parallelograms, right? We could use any one of these sets as parallel lines, and then from there we have two options for transversals. So just know that when we're talking about alternate angles and different shapes, really try to picture and look at what's happening in our figure so we can figure out what are examples of alternate interior angles. So what are alternate interior angles by definition? And then we can use the theorem that states that they're congruent. It's kind of like two steps. By definition of an alternate interior angle, these two angles, these are two alternate interior angles by definition. And then by the alternate interior angle theorem, they are in fact congruent, okay? And realistically, something else I guess that I should note is that the alternate interior angle says if we have parallel lines cut by a transversal, so that's kind of already including the definition, so we can kind of combine that into one step. Now, make sure that you understand what supplementary, linear pairs, and straight angles are. I know that I've talked about these in the videos for vocabulary, but I really want to make sure that you understand what they are so when I go in and use them in a proof, you can understand why I'm using them. Supplementary means they add to 180. Linear pairs are two lines that share a straight line, and a straight line is a line, right, that has 180 or that measures at 180 degrees. So a straight line is supplementary, or a straight line has supplementary pairs, which we call linear pairs. Hopefully that makes sense. So all of these are all related, and we need them when we're doing proofs with parallelograms. Okay, so parallelograms we know have parallel sides, two sets of parallel sides. But something else that's true about them is that their angles, opposite angles, are congruent. Now, how on earth do I know that that's true? To do this, let's first kind of ignore the theorem side of it, and let's just talk about it logically. What is happening in our figure that we have here? So we are told that angle 4 here, and let's see if I can get a color and cover this up. So that is angle 4 right here. And we are told that this angle measures at 105 degrees, okay? Measures at 105 degrees. Let's forget about the proof side and let's just figure out if we can identify the angles for all of our other values here, okay? So the first thing that I could look at, and the first thing that I always love to look at, is our vertical angle, because I don't have to do math. Vertical angles are congruent. So I can just automatically know that in here, B is a vertical angle, so it's 105 degrees. So I've got that taken care of. Now, another thing that I can get taken care of without having to do any math are our corresponding angles. Corresponding angles, remember, are in the same quadrant of our square when we put a square around our vertical angle or around our vertex, okay? And so basically here in my upper left and my lower right, we have 105 degrees, 105 degrees, okay? Now we've kind of taken care of everything on this transversal, but we can actually do the same thing here since these lines are also parallel. Specifically, because we have two sets of parallel lines, we can do this. We also have corresponding angles here and corresponding angles here. That means that we have 105 degrees basically in the upper left and the lower right of every single one. 105. I can't write 105. This little box. 105, 105, okay? By corresponding and vertical angles, we can identify that there's 105 degrees in each one of these like upper left and lower right quadrants. Now, how on earth do we find what the angle measure is for our 2 and our 3? Well, remember, we just talked about linear pairs, and linear pairs are two angles on a line that equals 180 degrees. We could talk in terms of this, we could talk about these ones being linear pairs, or we could talk about these ones being linear pairs, right? They're both working off of a line. So you can just pick one, right? Or you can do them kind of both at the same time, because if we're working with 105 degrees, right, there's only one possible answer for both of them. And to find that, we take our total of 180 degrees that our linear pair is equal to, we subtract it from 105, and then that gets us that our angle measure for our linear pair has to be 75 degrees. It has to be 75 degrees. Okay, so these are both linear pairs with our side 4, right? They're both 75 degrees. But guess what? Once again, because of corresponding angles, and even we could even talk about because of vertical angles, that means that all of these are 75 degrees. 75, 75, 75, right? Because these two are corresponding angles, these two are corresponding angles, right? These two are corresponding angles, these two are corresponding angles, these two are corresponding angles, right? We've got so many corresponding angles, but ultimately around each one of our vertices, when we draw kind of this four quadrant square, right? To identify our different quadrants, we have the same picture. Oops, I forgot one. We have our same picture in each one of them. They're basically just carbon copies of each other. Now, how does that apply to our parallelogram? I don't know if you can still see it, but in here is our parallelogram right here. Parallelogram, okay? And our parallelogram, we were trying to prove that the alternate angles, the opposite angles of each other, are congruent. Well, look, we've got 75 degrees on this line, and then we've got 105 degrees on this line. Those measures are equal to each other, so they're congruent to each other. Now, how do we formalize this in a proof? Well, we kind of are just going to explain what I just talked about and how I identified what each one of my angles are. In this case, okay, let me erase my little X mark that I made here. We're told that we have two sets of parallel lines. A and B are parallel to each other, and E and F are parallel to each other. And then we're told that this measurement right here of angle 4 is 105 degrees. That is information that we are given. We don't have to do any work to do it. Now, we basically just went, square by square to find the angle measures. However, in proofs, we want them to be as efficient as possible. So realistically, when we're working in our proof, we just want to know the angle measures of what is kind of in our parallelogram right here. So we want to solve for as many angles as possible without having to really go outside these 4 angles. Now I'm going to erase everything and then talk about this line by line. So we have our angle measure here that's 105 degrees, okay? And in order to kind of find our angle 6 here, they have chosen to talk about corresponding angles. Now remember, corresponding angles, same side of the square, same quadrant as the square. So they've decided to first identify that angle 4 and angle 8 are corresponding angles, and then they've come over here to this quadrant and they've talked about how angle 4 and angle 12 are corresponding angles, okay? So now we know the value, the measure of an angle in basically these 3 vertices. We've got a measure for each one of them. So by definition of corresponding angles, okay, we know that angle 4 and angle 12 are corresponding, and angle 4 and angle 8 are corresponding. This is one of those examples where they're doing the definition first, and then they're applying the postulate. So we know that these ones are corresponding. Then by the corresponding angle postulate, we know that they're equal. So first we know what they are, and then we know what they're equal. Up next, we want to find our kind of next round of angles. Remember, our goal is to get to know the value of 6, 11, and 13. So in order to find 6 and 11, we can look at linear pairs, just like we did before, okay? 6 and 11 are linear pairs with 12 and 8, okay? These are linear pairs with 12 and 8. What do we know about linear pairs? When we add them up, they equal 180 degrees. So by definition of a linear pair, if we add up 6 and 8, and if we add up 11 and 12, they equal 180 degrees. Now we have these lovely equations here. The measure of angle 8 plus the measure of angle 6 is 180. The measure of angle 12 plus the measure of angle 11 is 180. We can replace, because of the substitution property of equality, we can replace anywhere where we see an 8 with 105, and anywhere where we see a 12 with 105, because we've already said that these two angles are congruent to angle 4. They have equal measures. And remember, angle 4 is 105 degrees. So we're replacing anywhere where we see a measure of angle 8 with 105, and anywhere where we see a measure of 12 with 105. So now we've got these new equations that say 105 plus the measure of angle 6 is 180, and the 105 plus the measure of angle 11 is 180. And we've done that with substitution. So remember, what you need to know what is substitution so you can plug it in here for the reason. Now, let's move on to kind of our next step. And I'm going to have to, let's just erase this side here so I don't lose any of my work. Okay, so we've done the linear pairs, we've done the substitution. What do we do next? Well, we can use the subtraction property and take out 105 from each side. It's just like if we're solving multi-step equations where we subtract 105 from both sides. 105 from both sides, from the 180 and from the left side of our equation that has the 105 on it, right? This is the substitution property of equality that lets us, this is the subtraction property, not the substitution. This is the subtraction property that lets us subtract these values out from both sides. then we're left with basically what the measure of each one of these angles are. That means that 6 is 75 and 11 is 75. And look, we have our first congruence here. These two angles are equal to each other, which is like our first step in showing that opposite angles are equal to each other for both pairs. Now, the one thing that we don't know is what is the measure of angle 13. Now, we could use the alternate interior angle. You see we have our parallel lines and our transversal. We could use our alternate interior angle with 8 and 13, or we could do 12 and 13. Here, they've chose to do 12 and 13. So 12 and 13 are alternate interior angles by definition, right? We have parallel lines cut by a transversal. So this here is its alternate interior angle pair. The alternate interior angle theorem tells us that they are equal to each other. So that means that angle 13 is also 105 degrees. Now we have everything that we need to prove that opposite angles in a parallelogram are congruent to each other. We have 4 and 13 that are both equal to 105, and then we have 6 and 11 that are both equal to 75. Okay, that's a super long proof, but we're basically just taking what we did in the first steps, and then we are applying the words, the reasoning, why we're doing it to it. Okay, let's look at side congruence now. Side congruence is a much shorter proof, and we use something that we haven't quite talked yet about, which is the diagonal. So what they've done to set up this problem is we've got these sets of our parallel lines. A and B are parallel to each other. E and F are parallel to each other. And then they have this diagonal A and C that cuts through our parallelogram. Okay, this is all given information. Now, before we talk about the proof, okay, let's talk about what's happening. So we have parallel lines, and they're being cut by this transversal here, okay, this AC. Now, in this case here, right, so we've formed two triangles. We've been doing triangle congruence theorem for a while now, and we want to use those triangle congruence theorems to show that we have two congruent triangles and therefore can have corresponding parts. Because our goal is to show that opposite sides are not just parallel, but that they are congruent to each other. That is our ultimate goal when we're trying to identify that our sides are congruent. Now, we're not going to talk about numbers here. We're not going to talk about angle measurements. We're just going to talk about how do we know that specific angles and sides are congruent to each other. In this case here, okay, we have parallel lines and transversals. So we have alternate interior angles. You see both of these, all of these angles that we're working with here are inside our parallel lines. So they're parallel, or they're interior. And we can then look on either side of our transversal line to show that these lines are actually also alternate interior angles. Now, if I wanted to break this proof down more, actually, let's pause. I'm not finished talking. Then we'll talk proof. I promised I would do that. So we've got this alternate interior angles that shows that we have congruence in our angles. And then we can use the reflexive property to show that in this case, right, AC is congruent to itself. So we have angle side angle. That is exactly what we wanted. We wanted angle side angle when solving for this. Because if we have angle side angle, that means that my triangle ABC and CDA are congruent to each other. If we have congruent triangles, then the corresponding parts of them are congruent, which then, right, the corresponding parts of BC is corresponding to AD. So we've got these two sides that are congruent to each other, and AB and CD are corresponding, so that means that they are congruent to each other. So we've used a triangle theorem to show that our sides are congruent. How do we show that in a proof? Okay, So like I said, a lot of times I like to talk definitions first. In this proof, they have skipped the definition. So they start with our given information. And then normally I would say that, that angle 1 is equal to angle, well, I guess I could say angle 1 and angle 2. I wouldn't say equal. I would say angle 1 and angle 3, angle 1 and angle 3 are corresponding, right? Are corresponding alternate interiors, alt interiors, as well as 5 and 2. So angles 5 and 2 are alt interior, and this is by definition. So if we wanted to start with the definition, by definition, these angles are alternate interior. Now, by the alternate interior angle theorem, that's how we know that they're congruent to each other. Okay, they've kind of skipped it, they've kind of put it all in one, but that's how we know that they're congruent. We know by definition they're alternate interior, and then by the alternate interior theorem, angle theorem, we have congruent angles. So that means they're equal and same size, same shape, right? They're equal to each other, they're congruent. Okay, that gives us our first step. Now, after we found our alternate interior angles that are congruent, the next thing we wanted was this side right here. We're like, oh, we want angle side angle, so we're going to use the reflexive property to show that AC is equal to AC. That was our third step. Now, using angle side angle theorem, we have that these triangles are congruent to each other, and our last step was applying the CP-CTC theorem to show that these therefore are also congruent to each other. Okay, so we first kind of explained it, and then we formally wrote it down here in our 2-column proof. Okay, let's talk diagonals. I just talked about diagonals. Let's talk about them formally. Now, there's 3 things that we know about diagonals going into it. The intersection of the diagonals labeled at point O. O is the intersection. It's where they cross. Dependent on our figure, we are not guaranteed that the lengths of the diagonals are going to be equal. So, right, in this case, in our kite, right, these are 2 different lengths. So we're not guaranteed that the lengths are going to be equal. And we are not guaranteed that the lengths of the segments are going to be equal either. So we're not guaranteed that these are an even split. Basically, we're not guaranteed that they are a bisect. We're not guaranteed that they bisect each other. And you can kind of see that once again in kites. Kites kind of mess everything up. Okay, now let's look at a proof with diagonals specifically regarding parallelograms. Now, we want to show that when parallelograms have these diagonals, that they bisect each other. What that means is that DO and BO and AO and CO, right? So DO and BO are going to be equal to each other, and then AO and CO are going to be equal to each other. Okay, they bisect each other. Now, let's skip the proof again and let's just talk about what is happening in our picture. So we have parallel lines, and I'm going to switch up some colors here. So we've got parallel lines, we've got this DC, and we've got this AB that are parallel to each other by definition of a parallelogram, right? And then with our diagonals here, we've got this diagonal here of DB, and we've got this diagonal here of AC. Okay, so when we have parallel lines and we have a transversal, the first thing I can start to identify is our alternate interior angles. Alternate interior angles are always congruent, okay? And so I can look here at the line or the angle that's made with our ABO here, okay? This angle is going to be congruent to this angle, the alternate interior angles. Looking at our other transversal here, we've got our line, our angle ADC, this one right here, right? If we run along the transversal, the opposite interior angle is going to be this one right here, this ABD angle, or ABO if we want to use the O as one of our endpoints, right? So basically, and I should put double lines here. So basically using just our parallel lines and our two transversals, we can identify two sets of alternate interior angles. Okay, and remember our alternate interior angle theorem is what's going to tell us that those are congruent and therefore equal. Now, if I were to look at this triangle here and this triangle right here, right? We can see that we have two known congruent and corresponding angles. We want to show that these triangles are congruent to each other so that we can then apply that our bisectors are congruent also. And there is something, right, in the definition of, well, not in the definition of a parallelogram, but something that we proved before using the definition of a parallelogram, and that is that opposite sides are congruent. We just proved that opposite sides are congruent, so we can use that proof that we just proved to show that AB and CD are congruent to each other. And look at this. Now we have an angle, a side, and an angle that we are working with. That means that we have congruent triangles, and then we can use CP/CTC to then say, okay, if we have congruent triangles, then that means that all of our sides and all of our angles are congruent to each other. And then look at that. We can show that our angle or that our diagonals bisect each other. So we know by definition of a parallelogram that we have two sets of parallel sides. We've got AD and we've got CB that are parallel to each other, and then we've got DC and we've got AB that are parallel to each other. This is exactly what we're talking about, the perfect setup, right? Now, we know that we have a single line that crosses through these parallelograms, right? This is the transversal, and we use those transversals and the definition of alternate interior angles to show that BAC, this one here, is congruent to PCA. Right, so these two teal ones here are congruent. And then we can also use the fact that we have transversal and two parallel lines to show that BBA and we've got BCC, these two green ones here, are also congruent to each other. And that over here, we're just explaining that AC and DB are transversals of our parallel lines, and by definition, they're alternate interior angles, and alternate interior angles are congruent by the alternate interior angle congruence theorem. That's a lot of proof. I'd break that down into what I just talked about. However, this is all in one step. We know that these angles are congruent to each other. Now, opposite sides of parallelograms are always congruent, so that's where we get that these two sides here are congruent to each other, which gives us that triangle DOC and BOA are congruent because of side. So we've got that these two triangles are congruent, or by angle, side, angle. Once we have the congruence of a triangle, we can apply the CP/CTC theorem that shows that DO and BO are congruent, and that AO and CO are congruent. And because they're congruent, then we know that AC and DB are bisectors. So this is just everything we've talked about broken down step by step, almost step by step.